4 light-years away, a small red star burns quietly in the dark. It has 3 planets. One of them is the size of Earth, and we will probably never touch it. In this video, you will see a star that throws firestorms strong enough to peel a planet, a world locked in eternal twilight, a spacecraft idea the size of a postage stamp, and a journey that would outlive every person watching this. If cosmic mysteries pull you in, hit that like button and subscribe so you never miss what we uncover next. The closest star to our home is also the most impossible. Prepare yourselves. We begin. 4.2 light-years. That number sounds small. It feels almost reachable, like a long road trip across a continent. But the truth is something your mind will struggle to accept. Light travels at about 186,000 miles every single second. In 1 second, a beam of light could circle the Earth 7 times. That same beam, racing through empty space without slowing, without stopping, without resting, takes 4 full years and 3 months to reach Proxima Centauri. Now picture that distance in miles. 25 trillion miles. Write it out. 2, 5 and 12 zeros trailing behind. There is no human experience that prepares you for a number like that. Try a smaller comparison. The distance from the Earth to the Moon is about 240,000 miles. When astronauts went there in 1969, it took them 3 days. The Moon felt far. People wept watching the landing. Families gathered around small black and white televisions, holding their breath. 3 days, 240,000 miles. Proxima Centauri is 100 million times farther. Let that distance settle in your bones for a moment. If you could somehow stack 100 million round trips to the Moon, end to end, you would finally arrive at the doorstep of our nearest stellar neighbor. And that is the closest one. Everything else is farther. Here is another way to picture it. Imagine you shrink the entire solar system down until our home star is the size of a grain of sand sitting on your kitchen table. In that tiny model, the Earth would be a speck of dust orbiting just inches away. Pluto would be a few feet across the room. But Proxima Centauri, Proxima would be another grain of sand sitting in a different city, about 40 miles away. 40 miles. Between 2 grains of sand, that is the emptiness we are talking about. Astronomers call Proxima our closest neighbor, and that word, neighbor, is generous. In any reasonable human definition, nothing about this is close. It is simply less impossibly far than everything else in the sky. The fastest object humans have ever built is the Parker Solar Probe. It moves at around 430,000 miles per hour as it whips around our local star. Faster than any spacecraft in history, faster than anything we have ever launched. At that speed, you could cross the United States from coast to coast in about 25 seconds. How long would the Parker Solar Probe take to reach Proxima Centauri? About 6,700 years. Civilizations would rise and fall before that probe arrived. Languages would be born and forgotten. Entire countries would vanish from maps that have not yet been drawn. The pyramids of Egypt are about 4,500 years old. Imagine launching a ship today and people 2,000 years older than the pyramids finally seeing it touch down on a distant world. That is the cost of crossing what astronomers casually call our backyard. And the strangest part is this: even at 6,000 years of travel, we are still using the fastest machine we have ever made. There is no faster option waiting in a garage somewhere. Speed has limits, and we are bumping against them. But the limits get even stranger when you understand what a light year really measures. A light year sounds like a unit of time. It is not. A light year is a measurement of distance, the distance that light travels in 1 year of uninterrupted motion. And once you understand that, a problem starts to creep in. A problem that turns every science fiction movie into a fairy tale. Light is the fastest thing in the universe. Nothing with mass can ever catch up to it. Not a rocket. Not a missile. not a wish. Albert Einstein figured this out in 1905, and more than a century later, no experiment has ever proven him wrong. Light is the speed limit of reality itself. So when someone says Proxima Centauri is only 4 light-years away, the word only is doing some heavy lifting. Because that distance assumes you can travel at the speed of light, and you cannot. Nothing made of atoms can. Imagine a highway with a speed limit posted at 186,000 miles per second. Now imagine you are driving a bicycle on that highway. That is roughly the gap between human technology and the speed of light. Even our wildest theoretical engines barely scratch a tiny fraction of light speed. The fastest serious proposals top out at around 20%. And those are paper designs, sketches, dreams scribbled by physicists who freely admit we have no idea how to actually build them. So when you hear 4 light-years, do not picture 4 years of travel. Picture thousands. Picture tens of thousands. Picture entire human lifetimes stacked end to end, with a child born on launch day dying of old age before the ship has even crossed a quarter of the way. There is another deception hidden inside the term. Light years describe how the universe looked, not how it looks now. The light from Proxima Centauri that hits your eye tonight left that star more than 4 years ago. You are seeing a memory. A snapshot from the past. If Proxima Centauri exploded right now, this very second, you would have no way of knowing for over 4 years. That ghost light problem becomes much more dramatic for distant objects. When astronomers look at galaxies billions of light years away, they are not seeing those galaxies. They are seeing how those galaxies looked when Earth was still molten rock with no life on its surface. The universe is a museum where every exhibit is frozen in a different era. And here is where travel planning gets even harder. If you launched a ship toward Proxima Centauri today, you would be aiming at where the star used to be 4 years ago. Stars move, galaxies drift. Everything in space is shifting along complicated paths. Hitting a target across light years requires calculations that account for cosmic motion over thousands of years of flight. Miss your timing by a fraction, and your spacecraft arrives at empty space. The star has moved on. Your destination is no longer where you thought it was. The journey ends not with arrival, but with silence and drift in the dark, forever. Light years are not just big, they are deceptive in every direction. They flatten time, they hide motion, they lie about closeness, and the machines we have today are barely qualified to attempt any of it. To understand just how far behind we really are, you have to look at what our fastest probes are actually doing right now. In 1977, 2 small spacecraft left Earth and never came back. Voyager 1 and Voyager 2 were built to study the outer planets: Jupiter, Saturn, Uranus, Neptune. They did their job beautifully. They sent back photos that rewrote textbooks. They discovered moons and rings and weather systems no one had imagined. And then, mission complete. They kept going. Right now, as you breathe, Voyager 1 is more than 15 billion miles from Earth. It is the most distant object humans have ever built. A small piece of metal carrying gold records etched with greetings in 55 languages, drifting outward at 38,000 miles per hour. 38,000 miles per hour sounds fast. It is fast. Faster than any commercial aircraft. Faster than any bullet. Faster than anything most people will ever ride. And it is hopelessly slow. If Voyager 1 were aimed at Proxima Centauri, which it is not, it would take approximately 73,000 years to arrive. 73,000 years. The earliest cave paintings in France are about 30,000 years old. Voyager would need to travel for more than twice that span before reaching the closest star. Modern humans only became modern humans roughly 200,000 years ago. Voyager would chew through a third of our entire existence as a species just to make a single trip. And nothing about Voyager is slow by design. It is using gravity assists from massive planets to fling itself outward. It is doing everything physics allows with a chemical rocket and clever engineering. Voyager represents the absolute ceiling of what 1970s technology could achieve. Half a century later, we have not really improved. The Parker Solar Probe is faster, yes, but it is faster only because it is falling toward our local star. Gravity is doing the work. Out in the empty dark between stars, no gravity is pulling you forward. You coast at whatever speed you started with. Voyager will continue at 38,000 miles per hour, essentially forever, because there is nothing out there to slow it down. And nothing to speed it up, either. This is the brutal truth of interstellar travel. Speed in space is permanent. Whatever push you got at launch is everything you will ever have, unless you carry fuel for another burn. And carrying fuel means carrying mass, and carrying mass means you need more fuel to push that mass. The math collapses in on itself almost immediately. Voyager will outlive everyone who built it by an unimaginable margin. The engineers who shaped its metal panels are mostly gone now. Their grandchildren are old. But Voyager keeps moving, silent, cold, carrying a message no one will ever read. In about 40,000 years, Voyager 1 will pass within 1.5 light years of a star called Gliese 445, not Proxima Centauri, a different star in a different direction. The probe was never aimed at our nearest neighbor. It was aimed at the giant planets and then released to wherever physics took it. If aliens ever find Voyager, they will be holding a relic, like discovering a stone tool buried in a riverbed. Ancient, slow, beautiful in its primitiveness. And the star Voyager is creeping toward, the kind of small red star it might one day meet, is the same kind of star waiting for us at Proxima Centauri, which means understanding what awaits us there begins with understanding what red dwarfs really are. Picture our local star, yellow, massive, burning hot enough to melt steel from 93 million miles away. Now shrink it, cool it down, dim it until it glows a deep smoldering red. That is Proxima Centauri. A red dwarf is one of the smallest types of stars in the universe. Proxima Centauri is about 1/7 the diameter of our home star. If our local star were a basketball, Proxima would be a softball sitting beside it. Tiny by stellar standards, almost embarrassingly small. But small does not mean weak. Small means stingy. Small means slow. Small means a different kind of dangerous. If you could somehow stand on a planet orbiting Proxima Centauri and look up, the sky would not be the familiar blue of Earth. It would be a deep, dusky orange. The star itself would hang in that sky as a swollen red ember, casting shadows in colors you have never seen. Reds bleeding into rusty browns. Light that feels old before it even reaches your skin. Red dwarfs burn at much lower temperatures than our local star, around 5,400 degrees Fahrenheit on the surface compared to about 10,000 for our own. That is still hot enough to vaporize anything you could touch, but in stellar terms, it is downright chilly, a simmer instead of a blaze. Because they burn cooler, red dwarfs use their fuel slowly. Astonishingly slowly, our local star is expected to live about 10 billion years total. Proxima Centauri will keep burning for trillions of years. With a T, long after every other type of star in the universe has died out, red dwarfs will still be glowing in the dark. They are the marathon runners of the cosmos, the last lights to go out. In some ways that makes them attractive. A stable, long-lived star sounds like the perfect place for life to take root. Plenty of time for evolution to do its slow magic. Plenty of warmth to keep biology ticking along. But Proxima Centauri is not stable, not even close. Up close, this small red star is a violent, twitching, flaring monster. Its surface boils with magnetic activity. Sunspots cover huge portions of its face. Loops of plasma arc out into space and snap back like rubber bands made of fire. The star does not sit quietly in the sky. It convulses. It explodes. It throws fits. And those fits are deadly. A red dwarf this small has a strange habit. Its energy does not stay locked inside. The interior is convective from top to bottom, churning like a pot of boiling soup. That churning twists magnetic field lines into knots. When the knots snap, energy bursts outward in flares thousands of times more powerful than anything our local star produces. If you were standing on a planet in Proxima Centauri's habitable zone, you would not see one steady red sky. You would see a sky that occasionally flashed bright enough to burn your eyes from across hundreds of millions of miles. Stable on a 1,000-year scale. Lethal on a Tuesday afternoon. This is the star whispering in our cosmic neighborhood, the small, smoldering one our descendants might one day try to visit. And it has at least one Earth-sized world orbiting through that violent red light. A world we have a name for, a world we have started to study, a world with a problem. In 2016, astronomers announced a discovery that made headlines around the world. A planet had been found orbiting Proxima Centauri. Not a gas giant, not a frozen rock far from the star, a roughly Earth-sized world sitting in the habitable zone where temperatures might allow liquid water to exist on the surface. They called it Proxima B. For a brief moment, it seemed like the universe had handed us a gift, a second Earth, just 4 light-years away, close enough that future generations might one day visit, close enough to dream about, close enough to study with telescopes that already existed. Astronomers used a technique called the radial velocity method to find it. They watched Proxima Centauri very carefully and noticed the star was wobbling slightly. Something was tugging on it, something with enough gravity to make a star jiggle in place. After years of patient observation, the wobble revealed a hidden world, orbiting once every 11 days. 11 days. That is the entire year on Proxima B, a year shorter than 2 of our weeks. The planet sits incredibly close to its star, about 4.5 million miles away. For comparison, Earth orbits our local star at 93 million miles. Proxima B is more than 20 times closer to its star than Earth is to ours. Normally, that would mean instant death. A planet that close to our home star would be a scorched, lifeless cinder. But Proxima Centauri is so dim, so cool, so weak compared to our local fire, that the habitable zone has shifted inward. The zone where water can stay liquid is right next to the star itself. Proxima B just happens to be sitting there. The planet weighs at least 1.17 times the mass of Earth. It could be slightly larger and slightly heavier than our home, or it could be much larger depending on the angle we are viewing it from. The exact size and composition are still uncertain. We have not actually seen Proxima B directly in any telescope we have. What we have is math, wobbles, spectral shifts, the signature of a hidden world dragging gravitationally on its host, like detecting a fish in murky water by watching the ripples on the surface. But the dream of a second Earth started to crack almost immediately. Because Proxima B sits in a habitable zone, yes, but the zone around a violent red dwarf is not a safe place. The same closeness that lets liquid water exist also drowns the planet in radiation. The same gravity that holds it in orbit also locks it into a strange and unfamiliar configuration. The same star that warms it also throws solar flares strong enough to peel an atmosphere off in a single afternoon. Imagine living in a house with a fireplace so close you have to sit against the wall to avoid being burned. Now imagine that fireplace occasionally explodes. That is Proxima B's situation. There are reasons to be excited. The planet is real. It has roughly the right size. It might have water. It might have an atmosphere. It might, on a wildly optimistic day, have life. There are also reasons for despair. Because the flares from a red dwarf are not just inconvenient, they are world killers. In March of 2017, astronomers watching Proxima Centauri saw something terrifying. The star, which is normally too dim to see with the naked eye from Earth, suddenly brightened by a factor of 1,000. For about 10 seconds, this small red ember became visible to a casual observer in the southern sky. A burst of pure energy ripping outward in all directions. The flare lasted only moments, but its effect on anything nearby would have been catastrophic. A flare is essentially a giant explosion on a star's surface, caused by magnetic field lines snapping and releasing enormous amounts of energy. Our own local star produces flares all the time. They cause radio blackouts and beautiful auroras here on Earth. But our home star is large and stable. Its flares, while powerful, are diluted by 93 million miles of empty space before they reach us. By the time the radiation arrives, our atmosphere and magnetic field can mostly handle it. Proxima B does not have that luxury. The planet sits 4.5 million miles from Proxima Centauri. When the star flares, the energy hits Proxima B 20 times more intensely than the same flare would hit Earth, and red dwarf flares are not gentle. Some Proxima Centauri flares pack more energy than our home star has produced in its entire recorded history of observation. Imagine being a planet, peacefully orbiting in your warm little spot, when your star suddenly erupts with a blast of ultraviolet and X-ray radiation 1,000 times stronger than anything Earth has ever absorbed. Now imagine that happens regularly. Researchers using the Atacama Large Millimeter Array, a network of radio telescopes in Chile, monitored Proxima Centauri for years and found that powerful flares happen often, sometimes multiple times a day, sometimes spaced out over weeks. But they are constant background noise in the planet's life. What does that do to a world? The first casualty would be the atmosphere. High-energy radiation tears apart molecules in the upper layers of any gas envelope. Over millions of years, flares can strip a planet's atmosphere right off into space. If Proxima B started with an Earth-like atmosphere 4 billion years ago, there is a real possibility it has nothing left by now, just bare rock, baking under direct stellar fire. The second casualty would be water. Even if the planet originally had oceans, those oceans need an atmosphere to stay liquid. Without atmospheric pressure, water boils away into space. Mars once had rivers and lakes. It lost its magnetic field, then lost its atmosphere, then lost its water. A dry red desert is all that remains. Proxima B might have followed a similar path, just on a faster timescale. The third casualty would be any life that ever tried to develop on the surface. Simple cells can be destroyed by ultraviolet radiation. Complex life is even more fragile. The only refuge would be underground, or under thick ice. Deep oceans, if any remain, could shield organisms from the worst of the flares. But the surface itself would be sterile. And here is the strangest twist of all. Even if the atmosphere held, even if life found a way, the planet would still face another challenge, something built into its very rotation, something that would divide the world into two halves, so different from each other that they might as well be two different worlds entirely. There is a strange thing that happens when a planet orbits too close to its star. Over time, gravity itself reshapes the planet's rotation. It pulls and tugs and squeezes until one side of the world is permanently facing the star, while the other side is permanently turned away. The planet stops spinning relative to its sun. It becomes locked. This is called tidal locking, and it is almost certainly what has happened to Proxima B. Picture a world where one half is always in daylight, where the star never moves in the sky, where shadows never shift, where there is no sunrise, no sunset, no dawn, no dusk, just a single motionless red eye hanging in the same spot, hour after hour, century after century. Now picture the other half. Eternal night. The star has never been seen from this side, never will be. The sky is permanently dark, dotted only with distant stars. If you stood there long enough to look up, you would see Alpha Centauri A and B shining brightly in the distance, two yellow companions visible across light years, while your own star burned forever on the opposite hemisphere. Two worlds in one, a day side and a night side, forever frozen in place. The day side would be hot, continuously baked by Proxima Centauri's red light. Temperatures could climb above the boiling point of water, depending on the atmosphere. Any oceans on this side would slowly evaporate over thousands of years, drifting as vapor toward the cold side. The night side would be brutal. Without any starlight to warm it, temperatures could plunge hundreds of degrees below zero. Water vapor arriving from the day side would freeze instantly. Ice would build up in massive sheets, growing thicker and thicker as eons passed. A planet-wide glacier covering half the world. And between these two extremes, there would be a narrow band, a ring around the planet, where day meets night, where the star sits low on the horizon, perpetually setting and never setting at the same time. This twilight zone could be the only place on Proxima B where temperatures stay moderate, the only sliver of land where life might cling to existence, a ring of habitable terrain, maybe a few hundred miles wide, stretching all the way around the planet from pole to pole, bordered on one side by furnace, on the other by ice, a thin green ribbon, if green exists there at all. The wind patterns on a tidally locked world would be extreme. Hot air from the day side would rush toward the cold side. Cold air would slide back along the surface. Permanent storms would scream along the Terminator line. Anyone living on Proxima B would experience weather completely unlike anything on Earth. Not seasons, not cycles, just constant flow from hot to cold, every second of every century. This kind of world challenges everything we assume about habitability. Earth's life evolved under a cycle of light and darkness. Plants follow the sun. Animals sleep and wake with the rhythm of day and night. On Proxima B, that rhythm does not exist. Any life there would have evolved in conditions humans have no good way to imagine. A still-faced planet, half burning and half frozen, ringed by a corridor of perpetual sunset. And there is one more problem, because even that thin habitable ring may not be safe from what comes next. There is something most people do not know about stars. They breathe. A star is not a sealed ball of fire. It constantly leaks. Charged particles, mostly protons and electrons, stream outward from the surface in a continuous flow. This flow is called a stellar wind. Our own home star produces one. We call it the solar wind. It blows through the entire solar system at speeds of over 1 million miles per hour. Earth survives this constant assault for one main reason. We have a magnetic field. Deep inside our planet, a churning ocean of molten iron generates a powerful magnetic shield that wraps around the entire world. This shield deflects the stellar wind, sending most of it streaming harmlessly around us into deep space. Without that magnetic field, Earth would be a different place, probably a dead place. Billions of years ago, Mars had a magnetic field. It probably had a thick atmosphere. It almost certainly had liquid water on its surface. We can still see the dry riverbeds, the ancient lake floors, the eroded canyons cut by rushing water. Then the Martian core cooled. The magnetic field weakened, and the stellar wind began to peel away the atmosphere. Slowly at first, then faster. Over hundreds of millions of years, Mars lost almost everything. Today, its atmosphere is so thin that water cannot exist as a liquid on the surface, a dry, dusty, frozen ghost of a planet. Now imagine that process happening to Earth, and imagine it happening tens of thousands of times faster. That is what Proxima Centauri does to anything orbiting near it. The stellar wind from this small red star is far more intense than ours, partly because it is so much more magnetically active, and partly because Proxima B sits so much closer to the source. Studies suggest the stellar wind hitting Proxima B is 2,000 times stronger than the solar wind that hits Earth. 2,000 times. Even with a magnetic field as strong as Earth's, Proxima B would likely lose its atmosphere within tens of millions of years. Without a magnetic field, the timeline shrinks to a few million years, a geological blink of an eye. The planet has been orbiting Proxima Centauri for billions of years already. Whatever atmosphere it once had may be long gone. And here is the cruel irony. Earth's magnetic field exists because our planet has a hot, spinning, liquid iron core. That core is hot because Earth is large enough to retain primordial heat from its formation. Smaller planets cooled. Mercury cooled. Even some moons in our solar system once had magnetic fields and lost them. If Proxima B is similar in size to Earth, it might still have a magnetic field. If it is slightly smaller, the field may already be gone. We cannot tell from this distance. The planet is too dim, too lost in its star's glare for current telescopes to detect a magnetic signature directly. There is hope. Some studies suggest a thick enough atmosphere or an exotic kind of magnetic configuration could shield part of the surface. The twilight ring might still be protected by deep oceans or geological features. Life, if it exists, might be hiding from the storm. But every protective layer would need to be incredibly robust, because Proxima Centauri is not the only star in the system. It has company, and the company is dangerous in different ways. Most people picture stars as lonely, single points of light drifting through the dark by themselves. Our own home star is one of those lonely ones. No siblings, no partners, just us, orbiting alone in our quiet corner of the galaxy. But our home star is the exception, not the rule. Most stars in the Milky Way come in pairs, or triples, or even larger groupings, bound together by gravity, locked in slow waltzes that last billions of years. When you look up at the night sky, many of those single bright points are actually 2 or 3 stars too close together to tell apart with the naked eye. Proxima Centauri is one of those. It is the smallest member of a 3-star system called Alpha Centauri. The other 2 members are larger, brighter, and much more sun-like in character. They are called Alpha Centauri A and Alpha Centauri B. Together, the 3 stars form a complex gravitational dance that has been going on for billions of years. Alpha Centauri A is the largest of the 3. It is roughly the same size as our local star, perhaps slightly larger. It burns yellow-white, with a temperature very close to our home. From a planet orbiting Alpha Centauri A, the sky would look almost familiar to someone from Earth. Alpha Centauri B is smaller, cooler, more orange in color, about 85% the size of our star, still much brighter than Proxima Centauri, still capable of warming planets to comfortable temperatures if such planets existed in stable orbits around it. These 2 stars orbit each other in an elliptical path. At their closest, they are about as far apart as our home star is from Saturn. At their farthest, they swing out to roughly the distance between our star and Neptune. The full orbit takes about 80 years to complete. So Alpha Centauri A and B swing past each other once every human lifetime. And then there is Proxima. Proxima Centauri is the runt of the family. Much smaller than its 2 siblings, much dimmer, and it orbits at an extraordinary distance from them, while A and B circle each other in close, gravitational embrace. Proxima sits far out on the edge of the system, about 13,000 astronomical units away. That is, 13,000 times the distance from Earth to our home star. Proxima takes around 550,000 years to complete one orbit around the central pair. 550,000 years. Since modern humans first walked the savannah, Proxima Centauri has not finished even one trip around its siblings. For a long time, astronomers were not even sure Proxima was part of the system. It seemed too far away. Maybe it was just a passing star, a lonely red dwarf, wandering by coincidence in the same general direction. But careful measurements of its motion confirmed that Proxima is gravitationally bound. It does belong. It is just clinging to the outer edge of the family by the thinnest of threads. From Proxima B, the night sky would contain an extraordinary sight. 2 brilliant yellow-white stars hanging close together, far brighter than any star in our own night sky, yet still distant pinpricks compared to Proxima itself. 2 suns visible from a third sun's planet, a view no human has ever seen. But the dance of those 2 close stars is not just beautiful, it might also be deeply destructive. 2 stars locked together by gravity create a special kind of beauty and a special kind of problem. Alpha Centauri A and B orbit a common center of mass. Each one pulls on the other. Each one is pulled by the other. They trace out matching elliptical paths, weaving around an invisible point in space that lies between them. Like 2 dancers swinging each other around a fixed spot on the floor, at their closest approach, called periastron, the 2 stars come within about 1 billion miles of each other. That sounds like a vast distance. And it is. But for 2 full-size stars, swinging that close means their gravitational fields are deeply intertwined. Anything trying to orbit either star at that moment feels the tug of both. At their farthest separation, called apastron, the gap widens to about 3 billion miles. The stars feel a little more independent. A planet orbiting one of them would experience less gravitational interference from the other. This regular ebb and flow has been going on for billions of years. Here is where it gets strange. Imagine you are a planet orbiting Alpha Centauri A. You want to stay in a stable, predictable orbit around your star. Good. But Alpha Centauri B is also pulling on you, and it is not pulling from the same direction all the time. As B swings closer and farther, the direction and strength of its pull keep changing. This is what astronomers call gravitational perturbation, a constant, complex shoving from a second source. For a planet very close to its own star, the effect is minimal. The host star's gravity dominates. The second star is just background noise. But for planets in wider orbits, the perturbation can be brutal. Over enough time, it can throw planets out of stable paths entirely, hurl them into deep space, or send them spiraling into one of the 2 stars. Astronomers have calculated stable zones around Alpha Centauri A and B. There are regions fairly close to each star, where planets could survive long-term despite the gravitational dance. Around Alpha Centauri A, the stable zone extends out to about 3 astronomical units. Around Alpha Centauri B, it extends to about 2.5. Both are large enough to include the habitable zone. So in theory, both stars could host Earth-like planets in roughly Earth-like orbits. But farther out, in the unstable zones, anything would be tossed around like a leaf in a storm. And Proxima Centauri sits far, far beyond the unstable zone. How did Proxima get out there? How does it stay bound to a system that should logically have flung it away long ago? The answer is one of the small mysteries of stellar dynamics. Some astronomers think Proxima formed at a much closer distance and was gradually pushed outward over billions of years. Others think it joined the system later, captured into a wide, lazy orbit by chance encounters. Either way, Proxima now drifts at the very edge of stability. A slight perturbation, a passing star, the right gravitational nudge from a distant object, and Proxima could be freed from the Alpha Centauri system entirely. It would drift off into the galaxy as a solo traveler. The triple star family would become a binary. For now, the 3 stars dance together, the 2 big ones swirling close, the small red one watching from far away. But the dance has consequences for any planet trying to survive nearby. The first instinct when you hear about a triple star system is to imagine chaos. 3 suns rising and setting at different times, days that never end, skies that constantly shift, planets ripped apart by competing gravities. The reality is more nuanced, and in some ways more surprising. Planets can survive in triple star systems. We have found them, but the systems have to be arranged carefully. The geometry has to be just right. Most attempts to form planets in chaotic gravitational environments fail. The protoplanetary disks get torn apart. Material that would normally clump into worlds gets scattered before it can finish gathering. In the Alpha Centauri system, The arrangement is favorable, sort of. The two close stars, A and B, are far enough apart that each one can hold its own planetary disk during formation. Proxima, way out on the edge, is so distant that it might as well be its own separate system. From the perspective of Proxima B, Alpha Centauri A and B are just two bright stars in the sky, not gravitational threats, just lights. So Proxima B can exist. It has existed. It has been orbiting its red dwarf parent for billions of years, undisturbed by the distant binary pair. But survival is not the same as thriving. Even with a friendly geometry, planets in multi-star systems face challenges Earth has never had to deal with. The night sky never goes truly dark when there are 3 suns involved. Long-period climate effects can be triggered by the distant stars. Comets and asteroids in the system can be thrown onto strange orbits by the combined gravity of multiple stars, leading to more frequent impacts on planets. Imagine living on a world where, every 50,000 years or so, the gravitational alignment of 3 stars peaks in just the right way to perturb the outer reaches of your planetary system. A wave of comets is hurled inward. The skies fill with bright tails. Most miss your world. Some do not. Earth has had mass extinctions from rare comet and asteroid impacts. A planet in a triple system might face them more often. Then there is the question of formation. Some astronomers have suggested that planets in close binaries struggle to form at all. The combined heat and tidal forces of 2 nearby stars can prevent dust and ice from settling into planets. The fact that Proxima Centauri has not just 1 but at least 3 confirmed planets, despite being part of a triple star system, suggests that planet formation is more resilient than we expected, or that Proxima formed its planets in isolation long before the system reached its current configuration. What this means for life is an open question. Life on Earth needed billions of years of relative stability to evolve. Massive comet bombardments occasionally reset the clock by triggering extinctions, but those were rare. On a planet in a triple system, the cosmic environment might be too turbulent for complex life to ever fully take hold, or it might just shape life in unfamiliar ways. Bacteria thrive in chaos. They survive radiation, freezing, vacuum, and impact. A planet that gets pummeled regularly might still host microbes, multicellular life, the kind that builds eyes, and brains, and curiosity, might never get its chance. Of course, all of this is speculation. We have no proof of life beyond Earth. Just questions piled on questions. To answer them, we would have to actually go. And going requires solving a problem that has stopped every interstellar dream cold. Rockets work by throwing stuff backward. That is the basic principle. You burn fuel, the burning gas explodes out the bottom of your engine. The reaction pushes your spacecraft in the opposite direction. Simple, elegant, powerful enough to send people to the moon and probes to the outer solar system, and completely useless for interstellar travel. To understand why, you have to understand a brutal piece of physics called the rocket equation. The faster you want to go, the more fuel you need, but the more fuel you carry, the heavier you get. The heavier you get, the more fuel you need to accelerate that extra fuel. It is a vicious circle, and it spirals out of control very, very quickly. For a trip across the solar system, the rocket equation is manageable. We can build spacecraft, fuel them with enough chemical propellant to reach Jupiter or Saturn, and call it a successful mission. Voyager carried only a tiny amount of fuel and still escaped the solar system. Most of its speed came from gravity assists. For a trip to another star, the rocket equation becomes a nightmare. Let me show you what it would actually take. Suppose you wanted to send a small probe, the size of a refrigerator, to Proxima Centauri. You want it to arrive in a reasonable amount of time. Say 1,000 years. Not human-friendly, but at least not 70,000 years like Voyager. For that timeline, you need to reach about 1% of the speed of light. That is roughly 6.5 million miles per hour. How much chemical fuel does that require? more than the entire mass of the observable universe. That is not a typo. To accelerate a small probe to 1% of light speed using chemical rockets, you would need to start with a fuel tank weighing more than every star, planet, and grain of dust we can see in the entire cosmos. Chemical rockets fail at this scale because the energy they release per unit of fuel is tiny compared to what is needed. Burning hydrogen and oxygen, the most efficient chemical reaction we use in space, releases only a small amount of energy per gram of fuel. To go faster, you need to carry more fuel. To carry more fuel, you need bigger tanks. To accelerate bigger tanks, you need even more fuel. The numbers explode into absurdity within a few exchanges. The fundamental problem is the speed of the exhaust. Chemical rockets shoot their fuel out the back at around 10,000 miles per hour. To accelerate a spacecraft to 1% of light speed, you need exhaust traveling at a substantial fraction of light speed itself. Otherwise, the math collapses. This is why every interstellar travel proposal, seriously considered by scientists, involves moving away from chemical fuel entirely, either nuclear reactions, which release thousands of times more energy per gram, or antimatter, which is even more powerful, or external sources of energy, like lasers fired from Earth pushing on a sail. The dream of a chemical rocket flying to another star is just that, a dream. The physics will not allow it. Not now. Not in 10,000 years. The rocket equation does not care how clever your engineers are. So humans started thinking about alternatives. Wild alternatives. Some involved harnessing the power of atomic bombs, and one of those ideas almost made it off the drawing board. In the late 1950s, a group of American scientists sat around a table and proposed something that sounds insane today. They suggested building a spacecraft that would fly by exploding atomic bombs behind it. Not figuratively, literally. The plan was to drop a real nuclear weapon out the back of the ship, detonate it, let the blast wave slam into a massive pusher plate and ride the resulting shock forward through space, then drop another bomb, and another, and another. One every few seconds, each explosion adding more speed to the spacecraft. They called it Project Orion. The idea sounds absurd, but the math was not. Nuclear explosions release enormous amounts of energy, far more than chemical fuel could ever produce. If you could harness even a fraction of that energy for propulsion, you could build a spacecraft capable of crossing the solar system in months and reaching nearby stars in a matter of centuries. The scientists involved included some of the most brilliant minds of the era. Freeman Dyson, a physicist who would go on to dream up giant structures around stars, was one of the most enthusiastic supporters. Theodore Taylor, a nuclear weapons designer, helped lead the team. They were serious people, and they were serious about this proposal. Their designs varied in size, but some were enormous. The largest version of Orion would have weighed 8 million tons. It would have stood as tall as a 30-story building. It would have carried thousands of nuclear devices, each detonating in carefully timed sequences. A pusher plate the size of a city block would absorb the blasts, dampened by shock absorbers the size of grain silos. This was not a tiny probe. This was a ship designed to carry people, hundreds of them, possibly thousands, to Mars in weeks, to Saturn in months, to the nearest stars in roughly a century or two. For a brief window, Project Orion looked like it might actually happen. The United States government funded the research. Engineers built prototypes. Small models were tested using conventional explosives to prove the basic concept could work. The pusher plate technology was real. The math was sound. The dream was just barely within reach. And then it died. The reason was politics. In 1963, the United States and the Soviet Union signed the Limited Test Ban Treaty. It banned nuclear detonations in the atmosphere, in space, and underwater. Suddenly, the entire basis of Project Orion became illegal. The spacecraft was supposed to launch from the ground, detonating nuclear weapons in the atmosphere on its way up. With the treaty in place, that was no longer possible. Some advocates argued the ship could be assembled in orbit and only used for deep space travel. But by then, public opinion had also turned. The idea of riding atomic bombs to other planets, of leaving a trail of radioactive fallout across the inner solar system, no longer seemed heroic. It seemed reckless. Project Orion was shelved. The blueprints were filed away. Freeman Dyson later said it was the death of a true dream of space exploration. He believed Orion could have put humans on Mars by 1965 and on Saturn's moons by 1970. But the dream did not entirely die. Other propulsion ideas followed. Ideas that did not need bombs. Ideas that needed something even more exotic. Something that almost does not exist. Imagine a substance so powerful that 1 gram of it, if used as fuel, could push a spacecraft to a significant fraction of the speed of light. Imagine a substance that releases energy when it touches normal matter, converting both the substance and the matter into pure radiation. No leftovers, no waste. 100% of the mass becomes energy, exactly as Einstein's famous equation predicts. That substance is antimatter. And it is real. Every type of regular particle in our universe has a counterpart. Electrons have anti-electrons. Protons have antineutrons. When a particle meets its antiparticle, both annihilate in a flash of pure energy. No explosion in the traditional sense, just a burst of gamma rays as mass converts directly into radiation. The energy released is staggering. Combining 1 gram of matter with 1 gram of antimatter releases as much energy as detonating about 43 kilotons of TNT, roughly the same as a nuclear bomb, per gram of fuel. A spacecraft using antimatter as propellant could theoretically reach speeds that make every other propulsion technology look like a bicycle. Some calculations suggest antimatter rockets could push a small spacecraft to 10 or 20% of light speed. Proxima Centauri would be reachable in a few decades, not a few thousand years. A human crew could conceivably make the trip in their lifetime. So why has not anyone built one? Because antimatter is one of the rarest and most expensive substances in the known universe. We can produce antimatter. We have been doing it for decades in particle accelerators around the world. Facilities like CERN in Switzerland can create antiprotons and anti-electrons by smashing regular particles together at extremely high speeds. When the energy is right, antimatter pops into existence as part of the collision debris. The problem is the amount. In a year of running the most powerful particle accelerators on Earth, we produce a few billionths of a gram of antimatter. Total. Not enough to fuel a flashlight, let alone a spacecraft. Worse, antimatter is incredibly difficult to store. The moment it touches anything made of regular matter, it annihilates. You cannot put it in a bottle. You cannot keep it in a tank. The only way to store antimatter is to suspend it in magnetic fields inside a vacuum chamber, holding the particles in place using electromagnetic forces. The technology exists, but only for tiny amounts. Storing enough antimatter to fuel a spacecraft is far beyond our current capability. And then there is the cost. Producing 1 gram of antimatter using current methods would cost more than the entire gross domestic product of the United States, probably more. Some estimates put it at over $1 trillion per gram. For a real spacecraft, you would need many grams, possibly kilograms. The price tag is essentially infinite by today's standards. Some scientists believe that in the distant future, we might develop more efficient ways to produce antimatter, solar-powered factories in space perhaps, or new physics that lets us extract antimatter from the vacuum more easily, or even discover natural pockets of antimatter somewhere in the universe. None of these solutions exist yet. None are close to existing. Antimatter remains a beautiful, terrifying, completely unbuildable propulsion system. So researchers turned to a different idea, one that did not require carrying any fuel at all, one that worked with light itself. In 2016, a billionaire and a small group of brilliant scientists announced an audacious plan. They wanted to send a spacecraft to Proxima Centauri, not in centuries, not in millennia, in 20 years of travel time, plus 4 more years for the data to come home, a round-trip journey in terms of information of less than half a century. The project was called Breakthrough Starshot. The billionaire was Yuri Milner. The scientists included Stephen Hawking, who lent his name and credibility to the effort shortly before his death. Together, they proposed something so radical it sounded like fiction. The spacecraft would not weigh tons, or kilograms, or even grams. It would weigh about 1 gram total, smaller than a postage stamp, a tiny chip of silicon packed with cameras, sensors, communication equipment, and a power source attached to a thin reflective sail. That sail was the key. Instead of carrying fuel, the spacecraft would be pushed by light, a massive array of lasers on Earth, totaling about 100 gigawatts of power, would fire at the sail for a few minutes after launch. The light pressure on the sail would accelerate the tiny craft to approximately 20% of the speed of light. 20% of light speed is about 37,000 miles per second, faster than anything humans have ever built. Faster, in fact, than most of us can really comprehend. At that speed, the journey to Proxima Centauri would take about 20 years. Once the craft arrived, it would fly past the system, taking pictures and measurements during its brief flyby, then transmit the data back to Earth using its tiny laser communicator. 4 years later, those images would arrive in our solar system, processed by waiting telescopes. For the first time in history, a real plan existed for reaching another star in a human lifetime. But the plan is fragile in many places. The lasers needed are massive. 100 gigawatts is more power than most countries can produce. Concentrating that power into a single beam aimed at a 1-gram spacecraft for several minutes without losing focus requires precision beyond anything we currently build. The sail itself is a problem. It would need to be extremely thin, extremely light, and extremely reflective. If it absorbs even a small fraction of the laser energy, it will heat up and vaporize instantly. The material science required does not yet exist. The spacecraft electronics are another challenge. Cramming a working camera, computer, and communication system into 1 gram of total mass is at the edge of what microelectronics can achieve, and the system would need to survive 20 years of cosmic radiation, frozen temperatures, and complete isolation from any human help. A laser signal from Proxima Centauri, sent by a 1-gram spacecraft, would arrive at Earth as the faintest whisper. Detecting it would require enormous telescopes and very long integration times. Even then, the signal might be too weak to recover. Despite all these challenges, the project has been moving forward, slowly, with careful research. Some early sail prototypes have been tested. Some laser concepts have been refined. The team estimates the full system could be ready in 20 to 30 years. If they succeed, the first interstellar mission could launch sometime around the middle of this century. 20 years of travel. 4 years for the signal. By the early 22nd century, humanity might finally see Proxima Centauri up close. But even at 20% of light speed, the universe has dangers waiting in the dark. Space looks empty. It is not. Between the stars, in the regions we casually call interstellar vacuum, there is still stuff. Atoms drift everywhere. Molecules float in cold, scattered clouds. Specks of dust, smaller than the period at the end of a printed sentence, hang in the dark for millions of years. In any given cubic mile of interstellar space, there are very few of these particles. Some atoms here, a tiny dust grain there, maybe a small ice crystal somewhere else. Far less material than even the best laboratory vacuum on Earth. So sparse, it might as well be nothing. At normal speeds, this stuff is invisible. Voyager has been flying through interstellar dust for decades and has not been harmed. The particles drift past too gently, to do any damage. A small bump here, a few atomic interactions there. Nothing serious. But breakthrough Starshot will not be flying at normal speeds. At 20% of the speed of light, those harmless little dust grains become bullets. When a spacecraft moves at that velocity, it is not really moving through space in the conventional sense. It is plowing through space. Every atom in the path of the ship collides with the front surface at enormous relative speed. Even a single hydrogen atom hitting a spacecraft at 37,000 miles per second releases energy comparable to a small spark of electricity. That is just one atom. There are billions and billions of them along any interstellar route. A single dust grain weighing a fraction of a millionth of a gram hitting the spacecraft at 1/5 light speed releases energy equivalent to a small bullet. The impact is not a gentle nudge. It is an explosion. The dust grain vaporizes. The portion of the spacecraft it hits vaporizes. A tiny crater forms in the surface, potentially destroying critical electronics or punching through the sail entirely. Over a 20-year journey across 4 light-years, the Starshot probe will encounter trillions of such particles. Just stray atoms ablating away the front surface of the ship, layer by layer. The spacecraft can be designed with a sacrificial front coating that erodes slowly, without compromising the core systems. But the larger grains are the problem. Even one decent-sized impact, with a particle big enough to see under a microscope, could end the mission. The spacecraft is only 1 gram. The sail is incredibly thin. A single bullet hole in the wrong place, and the mission is over. Researchers have spent years studying this problem. Some have proposed using thicker shielding on the front of the ship, accepting the weight penalty in exchange for survival. Others have suggested that the spacecraft could rotate during flight, exposing different surfaces to incoming particles and spreading the damage. Still others have proposed flying through known low-density regions of space, picking interstellar routes that avoid dust clouds. None of these solutions is perfect. The particle problem might be the single biggest obstacle to actually reaching Proxima Centauri at high speed. Build the lasers, make the sail, pack the electronics, launch the craft, and then watch it disintegrate in a slow, steady erosion across 2 decades of flight. For human travel, the problem is even worse. A human-sized spacecraft has a much larger surface area. The chances of catastrophic impact rise dramatically, and the speeds being discussed, even for unmanned probes, are too dangerous for human bodies inside. But even if you survived the dust, time itself would do something strange to you. Einstein gave humanity a gift and a curse. His theory of special relativity, published in 1905, predicted that time does not flow at the same rate for everyone. The faster you move through space, the slower time passes for you relative to people who are standing still. For everyday speeds, the effect is too small to notice. A pilot flying around the world at 600 miles per hour ages about a microsecond less than someone sitting at home. Imperceptible, meaningless in daily life. But at relativistic speeds, the effect becomes enormous. If you could travel at 90% of the speed of light, time would slow down by a factor of more than 2. For you, a year of your time would equal more than 2 years of time on Earth. Your wristwatch would tick at half the rate of clocks back home. Your heart would beat at half the rate. Everything about you would slow down from the perspective of anyone watching from Earth. But you would not notice anything strange. Inside the spacecraft, you would feel completely normal. Time would seem to flow at its usual pace. Your watch would tick normally. Your heart would beat normally. The strange thing would only be revealed when you finally returned home and discovered that everyone you knew had aged faster than you. This is not science fiction. It has been measured. Atomic clocks flown on jets and spacecraft have come back showing tiny differences from clocks left on the ground. The effect is real. The math works. Time is genuinely flexible. For an interstellar mission to Proxima Centauri, time dilation becomes meaningful at very high speeds. At 20% of light speed, the effect is small. About 2% slower clocks aboard the ship. Not enough to make a real difference in the lives of the crew. But at 90% of light speed, things get serious. A trip to Proxima Centauri that would take about 4.7 years from Earth's perspective would feel like only 2 years to the crew. The astronauts would arrive having aged less than half as much as their families back home. At 99% of light speed, the difference grows enormous. The 4-year trip would feel like only 6 months to the travelers. A crew launching at age 30 would arrive at Proxima Centauri having aged barely past 30, while their children back on Earth would be approaching middle age. This sounds wonderful in theory, a way to make interstellar travel survivable. Send astronauts at near light speeds, let time dilation shrink their journey, and let them experience the trip in months instead of decades. The problem is twofold. First, reaching 99% of light speed requires staggering amounts of energy, vastly more than even antimatter could realistically provide. Second, the people left behind on Earth do not experience the same time savings. To them, the mission still takes years. They wait, they age, they pass away. The travelers return, if they ever return, to a world that has moved on without them. There is a deeper problem. Even messages from the ship cannot travel faster than light. Communicating with travelers moving at relativistic speeds becomes nearly impossible during the journey itself. A single conversation could span years from Earth's perspective. The travelers and the controllers might as well be in separate eras. And that communication problem becomes its own nightmare when the ship finally arrives. Imagine sending a text message to your friend. You hit send. 8 years pass. Then they receive it. Their reply comes back. 8 more years go by. Total elapsed time from the start of one conversation. 16 years. And that was just one exchange, one question, one answer. This is the reality of communicating across interstellar distances. Even at the speed of light, the absolute fastest signal the universe allows, a message from Proxima Centauri takes more than 4 years to reach Earth. Any response takes another 4 years to travel back. A single back-and-forth conversation eats up nearly a decade of real time. For human travelers, this changes everything about what a mission would look like. Picture an astronaut aboard a spacecraft heading toward Proxima Centauri. She is 2 years into a long journey. She wants to ask mission control a question. Something simple. Should she activate the secondary thruster or save the fuel for later? She records her message and beams it back to Earth using a laser communication system. The signal travels through space at 300,000 kilometers per second. 2 years later, the signal arrives at Earth. Mission control listens, debates, makes a decision, and sends back their reply. 2 more years pass while the answer crawls through space toward her ship. By the time she hears the response, she has been waiting for 4 years. The original decision is long since irrelevant. She had to act on her own. This is why every interstellar mission, if it ever happens, will have to be designed for total autonomy. No real-time guidance, no emergency calls home, no human in the loop helping make decisions. The spacecraft has to figure things out by itself, or fail. For robotic probes, the problem is less dramatic but still strange. Imagine the breakthrough Starshot probe finally arriving at Proxima Centauri. It flies past the planets, takes pictures, gathers data. Then it sends everything home using its tiny built-in laser. The transmission begins. 4 years and 3 months later, the first photons of data arrive at Earth. Astronomers gather in mission control. They have been waiting for 2 decades. Some of them were children when the project began. Some of the original team members have died. The images that finally appear on screens are pictures from a star system captured years ago by a probe that may no longer even exist by the time anyone sees what it sent. Every interstellar conversation is a conversation with the past. This is not just a logistical headache, it is a philosophical one. The universe imposes a fundamental limit on how connected we can be with anything far from us. The galaxy is too big for real-time communication. The speed of light is too slow. For more distant stars, the problem becomes laughable. A message to a star 100 light-years away takes a century to arrive. A round-trip conversation eats up 200 years. Any civilization hoping to talk to another civilization across galactic distances would have to design their communication around timescales of millennia. A single exchange might span the rise and fall of empires. There are people who think this is why we have not heard from aliens yet. Even if intelligent civilizations exist throughout the galaxy, they are spread so far apart that meaningful contact is nearly impossible. By the time a signal arrives, the senders may be long extinct. By the time a reply gets back, the original recipients may have moved on or died out themselves. Communication across the stars is a slow-motion handshake that almost never lands. But there is a way around this, a controversial way, a way that asks humans to give up nearly everything they know. If you cannot make the journey shorter, make the people last longer. This is the logic behind one of the oldest and most haunting ideas in interstellar travel, the generation ship. The concept is simple in theory. You build a spacecraft so large that it functions as a small, closed world. You launch it toward another star at the best speed your engines can manage. You fill it with a starting crew of humans. And then you wait. Not the crew. The crew will die. Their children will live their entire lives on board. Their grandchildren will be born, grow up, marry, work, and die without ever seeing Earth. Several generations will pass entirely inside the spacecraft. Eventually, a distant descendant of the original crew will look out a window and see Proxima Centauri growing larger as the ship finally approaches its destination. The journey takes hundreds, possibly thousands of years. The travelers experience it as their entire civilization. The destination is myth to most of them. A bedtime story passed down through generations. The engineering challenges are enormous. A generation ship has to be a closed ecosystem. Plants need to grow to produce oxygen and food. Water has to be recycled with near-perfect efficiency. Waste has to be processed and returned to the system. Every gram of material on board has to last for centuries. Nothing can be replaced from Earth because Earth is light years behind. Some proposals have suggested ships measuring miles in diameter, holding tens of thousands of people, with artificial gravity provided by rotation, vast hydroponic farms, recreational areas, and even cities. Others have proposed smaller ships with crews of only a few hundred people, relying on frozen embryos to provide future generations rather than continuous reproduction. Either way, the ethical questions are immense. The first generation, the ones who choose to board the ship, are making a choice. They know what they are signing up for. Maybe they are explorers, fascinated by the idea of building a new world. Maybe they are desperate, fleeing problems on Earth. Maybe they are idealists, dreaming of a fresh start somewhere among the stars. But their children did not choose. Their grandchildren did not choose. The fourth and fifth generations, born and dying inside metal walls, never saw a sunset on Earth. They never walked on grass. They never swam in an ocean. They never knew anything except the hum of life support systems and the slow drift through interstellar space. Is it fair to bring children into existence on such a ship? To raise them knowing they will never reach the destination? To give them no choice about whether they want this life? Philosophers have argued about this for decades. Some say it is no different from any other parenting decision. Parents always bring children into a world they did not choose. Others say it is fundamentally different, because the constraints of a generation ship are far more severe than anything Earth imposes. There is no escape, no alternative, no way to opt out and try a different life. There are also practical questions. What if the mission fails? What if the destination star turns out to be uninhabitable? What if a disease sweeps through the ship and kills everyone in the third generation, leaving children with no adults to raise them? Generation ships ask humans to gamble their entire lineage on a centuries-long bet. Most people would refuse, some would not, and there is another option, one that does not require continuous generations. Just one crew, frozen, sleeping, but sleep across centuries is its own kind of nightmare. In science fiction movies, astronauts climb into glowing pods, close their eyes and wake up at their destination decades later, looking exactly the way they did at launch. No aging, no memory loss, no problems. In reality, freezing a human being is one of the hardest biological challenges we have ever faced. The technology to perfectly preserve a person for centuries does not exist. We are not close. We are not even on the road to being close. Despite decades of research, no scientist has ever frozen a complex animal and successfully revived it. Not a dog, not a mouse, not a human. The problem is water. The human body is mostly water. Around 60% of your body weight is fluid, mostly inside cells. When water freezes, it expands and forms sharp crystals. Those crystals shred everything around them at the cellular level. Membranes burst, tissues tear. By the time a frozen body warms back up, the damage at the microscopic level is catastrophic. Some animals have figured out how to handle this. Certain frogs in northern climates produce special antifreeze chemicals that prevent ice crystals from forming inside their cells. They can freeze solid in winter and thaw out alive in spring. But humans do not have this ability. We are warm-blooded mammals. Our biology is built for stability, not survival through freezing. Scientists have tried using cryoprotectant chemicals to prevent ice formation. These are essentially antifreeze fluids that replace water in cells, allowing the tissue to cool to extremely low temperatures without crystal damage. The technique works for small samples. We can freeze sperm, eggs, and embryos. We can freeze small pieces of tissue. We can even freeze entire organs for short periods. But scaling up to a whole human body is a different problem entirely. The cryoprotectant fluids are toxic at the concentrations needed for full body preservation. The body is also too large to cool evenly. The outer layers freeze first, while the inner organs are still warm. By the time the center is cold, the outer tissues have already suffered freeze damage. Some companies offer to freeze human bodies after death, in the hope that future technology will be able to revive them. This practice is called cryonics. The customers pay large sums of money to have their bodies preserved in liquid nitrogen indefinitely. None of them have ever been revived, none of them ever will be, with current technology. The damage from the freezing process itself is so severe that bringing them back would require capabilities we cannot even imagine yet. For interstellar travel, the problem is even harder. We do not want to preserve corpses. We want to preserve living humans in a state where their biology pauses for centuries, then resumes when they arrive at their destination. Heart still beating slowly, brain still alive, just slowed down. Cells still healthy, just frozen in time. This is sometimes called suspended animation, to distinguish it from cryonics. And it is even more difficult to achieve. Slowing a human metabolism down to almost nothing for centuries without causing damage requires a level of biological control we have not yet developed. There is some hope. Researchers have managed to put pigs into a state of induced hypothermia for hours during emergency surgery. The animals are essentially clinically dead during the procedure, with no heartbeat and no breathing, and are then revived. But hours are not centuries. The technology has a long way to go. If we ever figure it out, generation ships become unnecessary. A small crew could be frozen at launch and woken up at arrival. But even if you survive the freezing, you still have to survive the trip itself. Space is full of light. Most of it is invisible. Most of it is dangerous. The space between stars is not just dust and atoms. It is filled with high-energy radiation streaming in every direction. Cosmic rays from distant supernovas, X-rays from collapsing stars, gamma rays from the most violent events in the universe. All of this radiation is constantly washing through interstellar space, Mostly invisible, mostly harmless to anything well shielded. On Earth, we are protected. Our atmosphere absorbs most cosmic radiation before it reaches the surface. Our magnetic field deflects more of it. By the time the radiation reaches you, the dose is so low that your body can repair the small amount of damage it causes. You can spend your entire life walking around in the open and accumulate barely any harm from cosmic rays. In low Earth orbit, the protection weakens. Astronauts on the International Space Station receive radiation doses about 10 times higher than people on the surface. Over a 6-month mission, an astronaut might absorb as much radiation as someone living on the ground for a few years. It is enough to slightly raise their long-term cancer risk, but not enough to cause immediate harm. Beyond Earth's magnetic field, the situation gets worse. Astronauts traveling to Mars would receive radiation doses much higher than those on the space station. A round trip to Mars and back could expose a crew to a significant fraction of their lifetime safe limit just from background cosmic rays. For interstellar travel, the numbers become genuinely terrifying. A spacecraft heading to Proxima Centauri would spend years, possibly decades, completely outside the protective bubble of any star. There is no magnetic field, no atmosphere, no shielding at all, unless you build it yourself. The crew would be bathed in cosmic radiation for the entire journey. Over a 20-year mission at high speeds, the radiation dose could reach lethal levels, not just elevated cancer risk, actually fatal. Crew members could suffer severe radiation sickness, organ failure, and death long before reaching the destination. The problem gets worse at higher speeds. As a spacecraft moves faster through interstellar space, it encounters more particles per second. The cosmic radiation effectively becomes more intense because the ship is plowing into it instead of just sitting there. At 20% of light speed, the radiation environment is dramatically harsher than for a slow-moving probe. Shielding helps, but shielding is heavy. Adding lead or water or other dense materials to absorb radiation increases the mass of the spacecraft, which means you need more fuel, which means the rocket equation comes back to haunt you. There is a trade-off between speed, mass, and survival. You can have any two of these, but never all three. Some proposals involve using magnetic fields generated by the spacecraft itself to deflect charged particles, similar to how Earth's magnetic field protects us. These artificial magnetospheres are theoretically possible, but require enormous amounts of energy to maintain. And they only protect against charged radiation. Neutral radiation, like gamma rays from distant supernovas, passes through magnetic fields, untouched. The crew would also face local radiation hazards. Onboard nuclear reactors, if used for propulsion or power, would produce radiation that needs to be shielded. Stellar flares from the destination star, especially a violent red dwarf like Proxima Centauri, could deliver lethal doses during the final approach. Surviving the dust is one problem. Surviving the cold is another. Surviving the radiation is another still. And there is one more invisible danger waiting in the dark. Between the stars, there is a thin soup of gas and dust called the interstellar medium. For most of human history, no one knew it existed. The space between stars looked black and empty, and so it was assumed to be black and empty. Astronomers eventually figured out that something was there by noticing that distant stars looked slightly dimmer and redder than they should. Something was absorbing and scattering their light along the way. That something is the interstellar medium, a vast, almost ghost-like mixture of hydrogen, helium, and trace amounts of other elements, scattered through the galaxy at incredibly low densities. There is only about 1 atom per cubic centimeter in most of interstellar space. Compared to Earth's atmosphere, that is essentially nothing. But the universe is enormous. Stretched across light years, even a near vacuum adds up to a substantial amount of matter. And for a spacecraft trying to cross those light years at high speed, the interstellar medium becomes a serious obstacle. The first effect is drag. Even a thin gas exerts some friction on anything moving through it. At slow speeds, the friction is negligible. At 20% of light speed, the cumulative drag over years of travel can actually slow a spacecraft down measurably. Engineers designing interstellar missions have to account for this loss of velocity in their calculations. The second effect is the impact problem we already discussed. Every atom and dust grain the ship encounters becomes a high-energy projectile at relativistic speeds. But there are more subtle dangers too. The interstellar medium is not uniform. It varies dramatically from place to place. Some regions are denser than others. Some contain clouds of cold gas where stars are being born. Some contain bubbles of hot, ionized plasma created by ancient supernova explosions. The local cosmic neighborhood is a patchwork of different environments, each with its own characteristics. The route from Earth to Proxima Centauri passes through what is called the local bubble. This is a region of relatively low-density gas that surrounds our solar system, carved out by ancient supernovas that exploded millions of years ago. The bubble is roughly 300 light-years across, filled with hot, thin plasma. We are flying through it constantly as our solar system moves around the galaxy. Inside the local bubble, conditions are favorable for spacecraft. Low density, few obstacles, relatively calm. But we are also near the edge of a smaller cloud called the local interstellar cloud. This denser pocket of gas is right next to our solar system, and we may pass through it in the future. If we do, the interstellar medium near Earth becomes more dangerous, more dust, more gas, more risk for any high-speed spacecraft. There are also magnetic fields to worry about. The interstellar medium is threaded with weak magnetic fields, mostly inherited from the supernovas that shaped it. These fields are not strong, but they extend over enormous distances. A spacecraft passing through can experience strange electromagnetic effects, especially if it carries any electrical equipment or magnetic shielding. And then there are cosmic rays. Even in the local bubble, cosmic rays are constantly streaming in from distant parts of the galaxy. Some of these particles are accelerated to almost the speed of light by violent events in the universe. When they hit a spacecraft, they punch through metal like it is paper, damaging electronics, damaging biological tissue, adding to the radiation dose the crew accumulates. The interstellar medium is sparse. It is also pervasive, and it makes every interstellar journey harder than it looks on paper. But arriving at the destination might be even harder than getting there. There is a problem with going fast. Eventually, you have to stop. This is one of the dirty secrets of interstellar travel. Accelerating a spacecraft to high speeds is hard. Decelerating it at the destination is just as hard. And the math is often even worse. Think about it this way. If you spend half of your fuel accelerating away from Earth, you are now moving very fast through space. You arrive at Proxima Centauri after years of travel. Now what? If you do not slow down, you fly straight past the star system at 20% of light speed. You get a brief glimpse of the planets, a few seconds of high-quality data, and then you are gone, hurtling out into the deeper dark, with no way to turn around. This is exactly what breakthrough Starshot would do. The probe is too small to carry fuel for deceleration. It would do a flyby of Proxima Centauri, snapping pictures during the few hours it spent in the system, and then continue on into the void forever. For a real mission, especially one carrying humans, you want to actually arrive. You want to enter orbit. You want to slow down enough to study planets in detail, possibly even land on them, and definitely have the option to come home. To do that, you need to decelerate. And deceleration takes just as much energy as acceleration did. If you used a certain amount of fuel to speed up, you need the same amount of fuel to slow down, which means doubling your total fuel load. But carrying more fuel makes the spacecraft heavier, which means you need more fuel to accelerate that extra fuel, which means even more mass at launch. The rocket equation, which already made the trip nearly impossible, becomes catastrophically worse when you include deceleration. There are a few clever ideas to get around this. One approach is to use the destination star itself to help slow down. A magnetic sail, made of huge loops of superconducting wire, can interact with the stellar wind of the target star, generating drag that decelerates the spacecraft. The faster you are moving, the more drag you create. Over many years of careful maneuvering, you can shed your speed without needing onboard fuel. Another approach is to use light pressure in reverse. If your spacecraft has a sail, you can angle the sail to use the destination star's light to push you backward. The same principle that accelerated you with lasers from Earth can decelerate you with sunlight at the target. The catch is that red dwarfs like Proxima Centauri are dim, so the light pressure available for braking is much weaker than it would be at a brighter star. A third approach is aerobraking, but this requires an atmosphere. If the target planet has a thick atmosphere, a spacecraft can dip into it and use atmospheric friction to slow down. This works for orbital insertion at Mars and other planets. But for interstellar speeds, the friction would be so violent that the spacecraft would simply burn up. The fourth approach is to bring along a second engine for deceleration. This is the most straightforward solution, and also the most expensive in terms of fuel and mass. Every option has trade-offs. None of them is ideal. For an unmanned flyby, none of this matters. The probe gets a brief look and disappears. But for any serious exploration of the Proxima Centauri system, slowing down is just as critical as speeding up. And we still have not solved either problem. Even if we did solve them, the destinations themselves keep getting stranger. In 1995, astronomers found the first planet around another sun-like star. The discovery shocked the world. By the early 2000s, exoplanets were being found by the dozens. By the 2010s, by the thousands. Today, over 5,000 confirmed exoplanets are catalogued, with thousands more candidates waiting for verification. Most of these planets are nothing like Earth. Most orbit different kinds of stars. Most are too hot, too cold, too gassy, or too strange for life as we know it. But every so often, astronomers find something unexpected close to home. In 2020, a team of researchers announced the discovery of a second planet around Proxima Centauri. They called it Proxima C. The discovery had been suspected for years, based on subtle hints in the data, but it took precision instruments and patient observations to confirm. Proxima C is very different from its inner sibling Proxima B. It is bigger, heavier, colder, farther from its star. The planet is roughly 7 times the mass of Earth, putting it in the category of objects astronomers call super-Earths. It might be a rocky world, like a larger version of our home planet, or it might be a mini gas planet, with a thick atmosphere of hydrogen and helium surrounding a smaller solid core. We do not know yet. The mass is what we have measured. The actual composition remains a mystery. Proxima C orbits much farther out than Proxima B. Its year lasts about 5 Earth years, which means it sits well outside the habitable zone of its dim red star. At that distance, temperatures on the surface would be far below freezing. Liquid water cannot exist there, at least not on the surface. The planet would be a frozen world, possibly covered in ice, possibly with a thick atmosphere keeping it slightly warmer than nothing. Why does Proxima C matter? Because it expands what we know about the Proxima Centauri system. Just having one planet was interesting. Having multiple planets of different types suggests a more complex history. Proxima Centauri formed with a proper planetary system, much like our own, rather than just a single lonely world. For astronomers, Proxima C is also tantalizing because it might be observable in ways Proxima B is not. The planet is farther from its star, which means it is easier to separate visually from the star's glare. Some early hints from the Hubble Space Telescope suggested a very faint object might have been directly imaged near Proxima Centauri, possibly Proxima C reflecting light from the star. The detection has not been confirmed, but if it is real, it would be one of the first direct images of a planet around another star. A direct image is a big deal. Most exoplanets are detected indirectly by their gravitational effect on their host star or by the way they block light during transits. Actually seeing a planet as a faint point of light in a telescope image is rare. It requires the planet to be far enough from its star that the star's overwhelming brightness does not drown it out. Proxima C might be in just the right position, far enough out to be visible, close enough to study in detail. If future telescopes can confirm it, we will have a direct glimpse of a world in another star system. For now, Proxima C remains a mostly theoretical entity, inferred from data, probably real, probably frozen, probably alone in its cold corner of the system. But it is not alone, because there might be a third planet too. In 2022, astronomers announced yet another planet around Proxima Centauri. This one is called Proxima D, and it is tiny. The planet is estimated to weigh only about a quarter of Earth's mass, smaller than Mars, smaller than Mercury, one of the smallest exoplanets ever confirmed around another star. Detecting such a small world from light years away is an extraordinary technical achievement. The signal in the data is so subtle that it took years of careful observation to tease it out. Proxima D orbits incredibly close to its star, so close that its year lasts only 5 days. 5 Earth days for one complete trip around Proxima Centauri. The planet whips around the star at high speed, locked into a tight, fast orbit. At that distance, the planet sits well inside the habitable zone, closer to the star than Proxima B. Temperatures on its surface would be high, possibly hot enough to vaporize water, possibly hot enough to melt some kinds of rock. Definitely not a place where life as we know it could exist. But Proxima D is interesting for other reasons. For one, it confirms that Proxima Centauri has at least 3 planets, a real planetary system with worlds of different sizes orbiting at different distances. This is not a fluke. This is a fully formed system, comparable in some ways to our own inner solar system. A small world, close to the star, an Earth-sized world in the habitable zone, a super-Earth out in the cold, a planetary buffet around our closest stellar neighbor. For another, Proxima D demonstrates how sensitive our detection methods have become. 20 years ago, we could only find massive planets orbiting close to bright stars. Today, we can detect Mercury-sized worlds around dim red dwarfs. The pace of improvement has been astonishing. With even more advanced telescopes coming online in the next decade, we may discover even more planets around Proxima Centauri. There could be a Proxima E, or F, or G hiding in the data somewhere. Worlds we have not yet noticed because our instruments are not quite sensitive enough. And there is something philosophically striking about Proxima D. The planet is so small, so close to its star, so apparently unremarkable, that under normal circumstances we would never have known it existed. From a distance of 4 light-years, detecting a Mars-sized object takes incredible precision. Imagine how many such tiny worlds must be hiding around other stars, just below our detection threshold. The universe might be teeming with small planets we cannot see yet. For visitors arriving at the Proxima Centauri system, Proxima D would be a quick stop, if it could be visited at all. The intense heat near the star, the radiation, the flares, all make it a hostile destination. It might be useful as a gravity assist for spacecraft maneuvering through the system, or as an observation post for studying the star up close, but not a home, not even a temporary one. What we have learned from Proxima D and from the system as a whole is that planet hunting is far from over. Every star out there, especially small dim ones like Proxima, probably has planets we have not yet found. The closest stars are no exception. Even our nearest neighbor, the star we have studied for over a century, kept secrets from us until very recently. Some of those secrets we still cannot fully see. Despite everything we know about Proxima Centauri, we have never actually seen one of its planets directly. Not really. The star itself is just a faint dot in our telescopes. Even with the most powerful instruments on Earth, Proxima Centauri appears as a tiny pinprick of red light, indistinguishable from a single point. Its planets, even smaller and dimmer, are completely lost in the glare. What we have, instead, are indirect detections, wobbles in the star's motion that betray the presence of orbiting worlds. Tiny changes in radial velocity as the star moves slightly toward and away from us, pulled by the gravity of its hidden companions. The wobbles are extraordinarily subtle. The star is moving only a few feet per second due to the gravity of Proxima B. Detecting that motion requires the most precise spectrographs ever built, capable of measuring changes in light wavelengths smaller than a millionth of a percent. The HARP spectrograph at the European Southern Observatory in Chile was the primary instrument for confirming Proxima B. It has been operating for over 20 years, slowly building up data on radial velocity measurements for thousands of stars. The Espresso spectrograph, an even more sensitive successor, helped confirm and refine the discovery. Both instruments are wonders of precision engineering, capable of measuring stellar motions that human senses could never detect. But measurement is not the same as imaging. For an actual image of a planet around another star, we need a different technique. Direct imaging requires blocking out the star's light, similar to using your hand to shield your eyes from our local star at sunset. With a special device called a coronagraph, astronomers can mask the star and reveal what is nearby. If there is a bright enough planet far enough from its host star, sometimes it appears as a faint speck in the image. Direct imaging works best for young, hot planets orbiting at large distances from their stars. These planets emit their own infrared light, making them easier to spot. Older, cooler planets, especially small rocky ones like Proxima B, are too dim and too close to the star to be imaged with current technology. There is one possible exception. Some studies using the Hubble Space Telescope found a faint signal near Proxima Centauri that might have been Proxima C. The signal was at the edge of detectability, and follow-up observations have not yet confirmed it. If real, it would be a rare direct image of a planet around our nearest neighbor. The James Webb Space Telescope, launched in 2021, has changed the game for studying nearby exoplanets. Its powerful infrared cameras can do things no previous telescope could. It cannot quite image Proxima B directly, but it can study the atmospheres of similar exoplanets around other red dwarfs. By doing so, it builds up our understanding of what worlds like Proxima B might look like. In the next decade, even more powerful telescopes will come online. The extremely large telescope in Chile, with a mirror over 30 meters in diameter, will have the resolution and light-gathering power to potentially image planets around Proxima Centauri directly. The Habitable Worlds Observatory, a future space telescope planned by NASA, may be designed specifically to find and study Earth-like planets around nearby stars. By the 2040s, we might actually see Proxima B, not as a wobble in data, not as a theoretical entity, as a faint, real, undeniable speck of light next to its red dwarf parent, the first direct glimpse of a world that until then has only existed in our calculations. But to know if it has an atmosphere, we need different tricks. When the James Webb Space Telescope launched, it carried something humanity had never had before: the ability to study the atmospheres of small, rocky planets around other stars. This is a big deal. Studying atmospheres is one of the most important steps in figuring out whether a planet might be habitable. A planet with the right atmosphere could support liquid water, regulate temperature, and possibly host life. A planet with the wrong atmosphere, or no atmosphere at all, would be inhospitable no matter how good its location looked from a distance. Webb works by observing exoplanets during transits. When a planet passes in front of its star, a small amount of starlight passes through the planet's atmosphere on its way to Earth. Different gases absorb different wavelengths of light. By comparing the star's spectrum before and during a transit, astronomers can detect the chemical fingerprints of whatever atmosphere the planet has. The technique is called transmission spectroscopy. It is incredibly difficult, especially for small, rocky planets. The amount of starlight passing through a planet's atmosphere is tiny. The signal is buried in noise. Even Webb, with its enormous infrared mirror and ultra-sensitive instruments, has to look very carefully to detect anything. Webb has been studying nearby rocky planets around red dwarfs since shortly after its launch. Some of its early targets have been the 7 planets in the TRAP-PIST-1 system located about 40 light-years from Earth. Like Proxima Centauri, TRAP-PIST-1 is a small, dim red dwarf. Its planets are roughly Earth-sized and tightly packed in close orbits. What has Webb found? Disappointing news for life enthusiasts. So far, the closest TRAP-1 planets that Webb has studied appear to have either very thin atmospheres or no atmospheres at all. The intense radiation and stellar wind from the red dwarf host star seems to have stripped away whatever atmospheres these planets started with. The worlds are bare rock, baking in the dim red light of their parent star. This is not great news for Proxima B. The conditions around Proxima Centauri are similar to those around TRAP-PIST-1. If TRAP-1's inner planets have lost their atmospheres, Proxima B probably has too. Years of bombardment by stellar flares, decades of erosion by stellar wind, billions of years of accumulated damage. The atmosphere may be gone, but not all the TRAP-PIST-1 planets have been studied yet. The outer planets, farther from the star, might have retained more of their atmospheres. They might still be hospitable. Or they might also be barren. Webb is slowly working through the system, one planet at a time. Proxima B is harder to study than the TRAP-PIST-1 planets because it does not transit its star from our perspective. We see Proxima B indirectly, through its gravitational pull, but it does not pass between us and the star. This means transmission spectroscopy will not work. Webb cannot observe Proxima B's atmosphere using the same technique it uses for TRAP-PIST-1. There are other ways to study the planet, but they are even harder. Direct emission spectroscopy, where the planet's own infrared light is captured and analyzed, might work in the future with more advanced telescopes. Polarization measurements, where the polarization of light reflected off the planet reveals information about its surface and atmosphere, are another possibility. For now, Proxima B remains a tantalizing mystery. We know it exists, we know its mass, we know its orbit. We do not know if it has an atmosphere, we do not know if it has water. We do not know if it has life. But once, just once, something strange came from that direction. In April of 2019, a radio telescope in Australia picked up something unusual. It was a narrow-band signal at a specific frequency, around 982 MHz. The signal lasted for about 30 hours, drifted slightly in frequency over time, and seemed to come from the direction of Proxima Centauri. The researchers analyzing the data called it Breakthrough Listen Candidate 1, or BLC1 for short. It was the first signal in the long history of the search for extraterrestrial intelligence that met all the technical criteria for what an artificial signal from another civilization might look like. For a moment, it seemed like everything had changed. The Breakthrough Listen project, the largest search for alien signals ever conducted, had been scanning the skies for years. It used powerful radio telescopes to listen to hundreds of nearby stars, looking for any signal that did not match natural sources. Most candidates were quickly dismissed as interference from Earth-based technology. Satellites, cell phones, microwave ovens, aircraft transponders. The sky is full of human-made radio noise, and most apparent signals turn out to be us. But BLC-1 was different. It came from the direction of Proxima Centauri. Its frequency drifted in a way that resembled what you would expect from a transmitter on a planet. It did not match any known Earth-based interference. It was, at first analysis, exactly what an alien signal from our nearest neighbor might look like. Researchers spent over a year carefully analyzing the data, looking for any natural or human-made explanation. They wanted to be certain before announcing anything. The history of the search for alien signals is littered with false alarms and embarrassing mistakes. No one wanted to be the next case study in scientific overreach. After extensive analysis, the verdict came in. BLC-1 was almost certainly not from Proxima Centauri. The signal turned out to be a form of radio frequency interference generated by terrestrial sources and processed in a way that mimicked an extraterrestrial origin. The drift in frequency, which had originally looked promising, was actually caused by the way the telescope was tracking the star. The narrow-band nature of the signal was characteristic of human-made electronics, not natural astronomical sources. For the researchers, it was disappointing, but it was also a valuable test. The discovery and analysis of BLC-1 demonstrated that the Breakthrough Listen project was working as designed. It could detect signals that looked like they might be alien. It could carefully investigate them. It could rule them out when necessary. This is exactly how the process is supposed to work. The episode reignited public interest in the question of whether anyone might actually be sending signals from Proxima Centauri. The answer, as far as we can tell, is no. We have not detected any confirmed artificial signals from our nearest stellar neighbor, or from any other star. The skies are silent in a way that some scientists find deeply puzzling and others find unsurprising. There are many reasons why we might not be hearing aliens. The universe could be empty of other civilizations. Life might be rare. Civilizations might destroy themselves quickly before they ever build powerful enough transmitters to broadcast across the stars. Or they might exist, but communicate using technologies we have not yet thought to look for. For now, the search continues. Proxima Centauri remains a top priority for any future signals from beyond, and the question of whether anyone lives there, in any form, remains unanswered. But the question of whether life could even exist there is darker than it sounds. For decades, astronomers have been excited about red dwarf stars as potential homes for life. The reasoning seemed solid. Red dwarfs are the most common type of star in the galaxy. They make up about 75% of all stars in the Milky Way. They live for trillions of years, far longer than our home star, giving plenty of time for life to evolve. Their habitable zones are easy to study because they are close to the star, making nearby planets easier to detect. If you wanted to find alien life, red dwarfs seemed like a good place to start, but over the past decade, the optimism has faded. As we have learned more about what life actually requires and what red dwarfs actually do, the picture has grown darker. The first problem is the flares. As we have seen, red dwarfs are violently active stars. They produce flares far more powerful relative to their size than larger stars. Their planets are bombarded with radiation that would strip atmospheres and sterilize surfaces. The youngest red dwarfs are the worst, blasting their newborn planets with radiation for hundreds of millions of years. By the time the star calms down, the planets may have already lost everything important. The second problem is tidal locking. As we have seen, planets in the habitable zone of a red dwarf are forced into permanent day-night configurations. One side cooks, the other freezes. The narrow twilight zone between them might be habitable, but it is a thin strip of land hemmed in by extreme environments on both sides. The third problem is ultraviolet light. Red dwarfs emit a lot of high-energy ultraviolet radiation, especially during their active periods. Ultraviolet light is bad for biology. It damages DNA. It breaks apart organic molecules. It would make life on the surface of a red dwarf planet very difficult to sustain. The fourth problem is photosynthesis. Plants on Earth use visible light to convert carbon dioxide and water into sugars. Red dwarfs produce most of their light in the infrared, which is too low energy for normal photosynthesis. Any plants on a red dwarf planet would need radically different biochemistry to harvest energy from the star. Some scientists have speculated that infrared photosynthesis might be possible, but no example of it exists on Earth. The fifth problem is timing. Red dwarfs take a very long time to settle into stable behavior. Their first billion years are turbulent and dangerous. Most habitable zone planets around red dwarfs would be in serious trouble during this early period. By the time the star calms down, the planet might already be a dead, atmosphereless rock. So why do we keep looking at red dwarfs? Because they are abundant, because they are close, because they are easy to study. Because even if most red dwarf planets are uninhabitable, there might be a few that are not, and those few would be the closest possible homes for life beyond Earth. The TRAPPIST-1 system, as we have seen, looks increasingly grim. Its inner planets seem to have lost their atmospheres. Its outer planets are too cold to host liquid water on their surfaces, at least without some heat source. The system, which seemed promising a decade ago, is now considered much less likely to host life. Proxima B is in a similar situation. The planet has the right size and the right distance, but the violent flares from its host star, combined with the powerful stellar wind, make survival difficult. The planet might be barren. It might still be habitable in the right protected niche. We do not know yet. To find out, we would have to go, and going is going to take far more than we currently have. How much energy does it actually take to send a spacecraft to another star? The answer depends on what you want to send and how fast you want to get there. But even the cheapest possible interstellar mission requires energy on a scale that humanity has never produced. Let us start with Breakthrough Starshot. That mission, which sends a 1-gram probe at 20% of light speed, requires laser power of about 100 gigawatts to push the spacecraft for several minutes. 100 gigawatts is roughly the entire electrical generation capacity of a small country. To run those lasers for the duration of the launch phase requires energy equivalent to what tens of millions of homes use in a day. That is for a single gram, for a probe smaller than a postage stamp. If you wanted to send a heavier spacecraft, say a refrigerator-sized probe with full instruments and communication equipment, the energy requirements scale up dramatically. A 1-ton probe would need many thousands of times more energy, possibly more than the entire annual electrical production of the United States. For a single launch, if you wanted to send humans, you are looking at energy demands that dwarf everything humanity currently produces, combined. A small crew of astronauts in a properly shielded spacecraft, with life support and decelerating engines, could require energy comparable to what our entire civilization uses in centuries, all concentrated into the launch and travel phases of a single mission. This is why some scientists have started talking about civilizations in terms of energy mastery. A famous classification developed by Russian astronomer Nikolai Kardashev in the 1960s defined civilizations by their ability to harness energy. A Type 1 civilization can use all the energy available on its home planet. A Type 2 civilization can use all the energy of its home star. A Type 3 civilization can use all the energy of its home galaxy. Humanity is not even Type 1 yet. We currently use about 10,000 times less energy than what is available to us on Earth. We are barely a Type 0.7 civilization by some estimates. We have not even mastered our own planet, let alone our star. To routinely send spacecraft to other stars, especially with humans on board, we probably need to be at least a Type 2 civilization. We need to be harvesting most of the energy of our own star. We need to be building megastructures to collect that energy. We need to be operating on scales that dwarf anything we currently do. Some scientists have proposed structures called Dyson swarms, arrays of solar collectors that surround a star and capture its entire output. Building one would require disassembling planets to get the raw materials. The infrastructure project would dwarf anything humanity has ever attempted by trillions of times. But the energy gain would be enormous. Once a civilization had access to a fraction of a star's output, interstellar travel would become much more feasible. We are very, very far from being able to do any of this. Some estimates suggest that humanity might reach Type 1 status in a few hundred years, assuming we keep growing our energy use at historical rates. Reaching Type 2 might take thousands of years more. Reaching the point where interstellar travel is routine, where ships move between stars the way our ships move between continents today, could take tens of thousands of years of continuous technological development. If anything goes wrong, if we never solve our current problems, if we never figure out sustainable energy, if we never build the necessary infrastructure, we might never reach the necessary level. The closest star could remain forever out of reach. But there are reasons to hope, cautious reasons. When will humans actually go to Proxima Centauri? The honest answer is that no one knows. The honest answer might also be never. But if you push scientists for a serious estimate, looking at how technology has developed and how it might continue to develop, you can sketch out a rough timeline. Not a promise, not a prediction, just an educated guess based on where we are now and where we might be heading. In the near term, meaning the next 20 to 50 years, the most likely scenario is that we send unmanned probes. Breakthrough Starshot, or something like it, could launch sometime around the middle of this century. The technology required is challenging but not impossible. The cost is high but not absurd. If the project succeeds, the first interstellar mission might be on its way before the end of the 21st century. But Starshot is just a flyby. 24 years of waiting, 4 years of data transmission, and a brief glimpse of the Proxima Centauri system at most. Not a real exploration, just a postcard from the dark. For a more comprehensive mission, with deceleration and detailed study, we need better propulsion technology. Some kind of fusion drive, perhaps. Or a refined magnetic sail. Or laser sails with the ability to slow down at the destination. These technologies might be developed within a century or two if research continues at a steady pace and if there is enough investment. A century or two means deep into the 22nd century at the earliest, possibly the 23rd or 24th century before we have spacecraft capable of doing real science at Proxima Centauri. For human missions, we are looking at much longer timescales. Sending people requires solving cryogenic sleep, or building generation ships, or developing exotic propulsion that lets us reach high speeds with massive cargo. None of these challenges have credible solutions on the table. Most experts who think seriously about this estimate, that human interstellar travel is at least 300 to 500 years away, some say 1,000 years, some say it might never happen. The optimistic scenario looks something like this. By the year 2100, robotic probes have reached Proxima Centauri and sent back detailed images of its planets. By 2200, more sophisticated missions are studying nearby stars in real detail, using interstellar fleets of probes equipped with advanced propulsion. By 2300 or 2400, the first crewed missions, in some form, begin tentative journeys to nearby stars. By the year 3000, if everything goes well, humanity might be a star-faring civilization. We might have permanent settlements around other stars. We might have crossed not just to Proxima Centauri, but to dozens of nearby systems. We might be the kind of civilization that science fiction has imagined for centuries. The pessimistic scenario is much darker. In the pessimistic scenario, we never solve the fundamental problems. Our civilization collapses before we develop the necessary technology. Climate change, war, resource depletion, or some other disaster ends our ability to dream big. We never leave the solar system. We never visit our nearest neighbor. The dream of touching another star dies with us, or with our distant descendants. The realistic scenario is probably somewhere in between. We make progress in fits and starts. We solve some problems and create new ones. We launch a few probes. We learn a few things. We never quite achieve the breathtaking interstellar exploration that science fiction promised, but we do not entirely fail either. We become the species that knew about other stars but could not quite reach them. Whatever happens, the people who go will pay a price the rest of us never have to think about. Imagine being told you can go to another star, but you can never come back. You will leave Earth. You will leave everyone you know. You will fly through the dark for years or decades or centuries. If you survive, you will reach a planet around another star. You might walk on that planet's surface. You might be one of the first humans to do so, but you will never see home again. This is the deal for any realistic interstellar mission. The technology to bring travelers back to Earth, at least in a reasonable amount of time, simply does not exist. Even if you arrived safely at Proxima Centauri, the return trip would take just as long as the outbound journey. By the time you got back, decades would have passed. Most of the people you knew when you left would be dead. The Earth itself would have changed in ways you cannot predict. For unmanned probes, this does not matter. Machines do not have family. They do not have homes. They do not feel loss. For human crews, the one-way nature of an interstellar mission would create psychological challenges unlike anything explorers have ever faced. Consider what astronauts already deal with on shorter missions. On the International Space Station, crews typically stay for 6 months. Even that limited duration produces significant psychological strain. Isolation from family and friends. Confinement in a small space. The strange feeling of looking down at Earth and knowing you cannot just go home. Astronauts have developed coping strategies. They keep in touch with family through video calls. They have regular contact with mission control. They know that in 6 months they will be back home hugging the people they love. Interstellar travelers would have none of this. The communication delay would make real-time contact impossible. Family would age decades while they were away. By the time any message arrived, the people who sent it would be older, or different, or gone. The travelers would be locked into a kind of permanent farewell, unable to fully engage with the world they left behind. Then there are the dangers of the mission itself. Knowing that you are years from any possible rescue, that if something goes wrong, no one is coming to help. That you have to handle every emergency with the resources you brought, because there is no resupply, no second chance, no backup. The constant low-level awareness of vulnerability would weigh on anyone, even the most resilient people. And then there is arrival itself. When you finally reach the destination, what do you find? Maybe a habitable world, maybe a barren rock, maybe success, maybe failure. If the planet is uninhabitable, the mission becomes an extended death sentence. The crew dies slowly in their spacecraft, with no realistic hope of survival, broadcasting their final messages back to an Earth that will not receive them for years. Researchers who study astronaut psychology have started to think seriously about the mental challenges of long-duration missions. They worry about depression, anxiety, sleep disorders, interpersonal conflict, and existential despair. All of these problems would be magnified for an interstellar crew, possibly to levels that no one has yet experienced. Some thinkers have suggested that interstellar missions should be crewed by people specifically selected for their psychological resilience. Others have suggested that the missions should include not just astronauts, but entire family units, so that crew members are not separated from loved ones. Still others have suggested that we should not send humans at all, because the psychological costs are too high and the practical benefits too uncertain. But humans will probably go anyway. Some of us will choose this journey, even knowing what it costs. The chance to touch another star will draw people in, even when the price is everything. And the meaning of that choice is the final question. For all of human history, the stars have been distant lights. We have looked up at them and wondered. We have named them. We have built religions around them. We have used them to navigate our ships and plant our crops, but we have never touched them. We have never been to them. They have remained eternally, just out of reach. Proxima Centauri represents the very first time in human history that another star might actually be reachable. Not easily, not soon. not without enormous cost and difficulty, but, in principle, possibly within our lifetime as a species. The closest star is a step we could plausibly take if we choose to invest the resources and develop the technology. What would it mean to actually take that step? The most immediate meaning would be scientific. Reaching Proxima Centauri would let us study another star system in detail, for the first time. We would learn about how planets form, how red dwarfs work, how life, if there is any, develops in environments different from our own. Every aspect of astronomy would be transformed by having direct access to even one other planetary system. But the deeper meaning would be philosophical. Throughout history, every time humans have crossed a major barrier, our understanding of ourselves has changed. The first ocean voyages revealed that the world was bigger than any single culture. The first moon landing showed us that other worlds were real places, not just lights in the sky. Each step outward has expanded what we consider home and what we consider possible. Reaching another star would do something even more profound. It would prove that humanity is not just a species confined to a single planet. We would be a species capable of moving between stars, a species capable of bridging the gaps in the universe that we once thought impossible to cross. It would also change our sense of timescales. We currently think in human lifetime scales. A year, a decade, a lifetime. If we have to plan missions that take centuries, with results that come back to descendants we will never meet, we have to develop new ways of thinking about purpose, new ways of investing in projects that we ourselves will not live to see complete. This is a kind of patience humanity has never really had to develop. Cathedrals took generations to build, but they were always still on Earth, still part of the world we knew. Interstellar missions would be different. They would require us to commit to projects whose results we could not see, on behalf of futures we could not imagine. There is also a sense in which reaching Proxima Centauri would be a kind of resurrection. Once we begin, once we send out crews or probes or seeds across the dark gap between stars, we begin to put pieces of ourselves into a much larger story. Our descendants, on another world, would carry forward what we are. The stars themselves would no longer be just abstract lights. They would be places where humanity has gone, where humanity has died. And then there is the question of finding company. If we go, we might discover that we are not alone. The universe might be full of other intelligences, hidden behind the same barriers of distance that have kept us apart. Or we might discover that we are, in fact, the only ones. Either answer would change everything. Right now, no one knows when we will go. No one knows if we will go. The closest star sits just 4 light-years away, mocking us with its proximity and impossibility. Visible to anyone who looks south from the right latitude on Earth. A small red dot, faint in the sky, the doorway to everything we have ever dreamed and feared. And maybe, one distant day, the doorway will open.